be. Okay, welcome to Organic Chemistry 2341 here on on a warm Thursday morning. Actually, I went outside today, it was already warm. So apparently it's going to get cold again, so don't get used to this. All right. So the first thing I want to say is, unfortunately, it looks like I forgot to do the second half of Module 2, which is IR spectroscopy. And since that is going to be due on Monday, I thought I better cover it today so you'd have at least an idea of how to assign that. So the end of the reading chapter on section 2 starts off with a module called IR spectroscopy or infrared spectroscopy. And so what I want to do is I want to go over that module today to make sure that you understand it correctly. So the thing I like about organic IR spectroscopy, putting it right here, is because, let me go to a different view here. Let me go to gallery view, there we go. Is because we just learned all these functional groups, right? And so we learned the different structures of the functional groups and how to name them and what they look like. Well, this is a great tie-in because IR spectroscopy is one of the best ways to understand how functional groups look and how they change from one thing to another. Meaning that when we take an IR spectrum of a compound, we can say, oh, look, there's a double bond. Oh, look, there's a carbonyl. Oh, look, that's an ester or an alcohol or everything. So all these functional groups we just showed can be represented by these different things. So I'm going to go ahead and share my screen and move this up over here to gallery mode. And there we go. I'm going to move this over here. All right. Can you see this thing saying IR spectroscopy?
Yes.
Okay, excellent. So the thing to remember about infrared spectroscopy is we're looking at electromagnetic waves, okay? And so in an electromagnetic wave, as it's going in a direction, it has an electronic version of the wave and a magnetic field generated by that in an orthogonal direction. So in physics, we use that, what we call the right-hand rule. And so you have the direction of the material, the direction of the electric field, and the direction of the magnetic field wrapping around it. So the cool thing is that different bonds can interact with that electric and magnetic field to vibrate. And when they interact with that specific wavelength at a specific energy, they will be absorbed. And we can see this absorption by saying, oh, that bond, that type of bond is there because it absorbed that specific kind of energy. Okay, so IR or infrared is just above red on the electromagnetic spectrum as we increase wavelength. So IR is a longer wave than the visible spectrum, and it's also decreasing in energy. So if you can look on here, the energy increases as we go from right to left. The wavelength increases as we go left to right. So IR is just a little bit less energy than the visible spectrum, but that means it's down in the energy range where it will start to absorb these light waves and start to vibrate. And that's what's really happening here. Okay, so one of the cool things about the new infrared technology, spectrophotometers, is the fact that they don't just take one pass through the material, they actually take multiple scans of that material and then they lay them all on top of each other so that you get a very clear, crisp, clean spectrum. And so what that would look like is something like this, where we have our, okay. All right, I cannot annotate on these slides for some reason. It's on Google Drive for some reason. So we start with this one right here on the left side here. It says coherent light source. And what that does is that means that it is put into a, it's all in one phase. And then it goes through the beam splitter and the sample, and then it gets detected. Now, what does it mean to get detected? What it's doing is it's measuring the light energies that are there and the light energies to there. Ooh, that's a great idea. Let me see, Sheila just mentioned I could download it from the track site. So let me do that, the Canvas site. Nope, not that. So let me stop sharing for just a second. I really want to annotate because it really, I think, makes a lot more sense when I do that. TX state. Oh, goodness. So, okay. Menu, faculty, Canvas, login. So, see, so what I do is I download my slides on my iPad with as a PDF file, and then when I have it as a PDF file, I get to annotate on my iPad, which is really cool. Go. All right. And of course, I have to unmute my phone, so it'll allow it to do the ping, do a push here. There we go. So, okay, let's see. Again, I apologize that this was supposed to be on my iPad last night, but it wasn't. Resources. No. Back. It's the really big one. I think it's that one. Nope. Oh. And now this won't go away. No, oh, there it is. No. Close. Why won't this go away? This won't close. My goodness. No, I am so sorry about this. Okay, what we're going to do is I'm going to try to lecture off of that Google Doc. I'm sorry about that, but okay, my iPad just restarted. So I'm going to pull the file up on my computer and share it from there. Wow. All right, that is not how I wanted to start my Tuesday morning. Okay, new slides. Okay, that's what we're going to do. We're going to close that. We're going to narrow this. Okay, at least I can share my slide and you can see my cursor moving. So let's do that. Acrobat Reader. Okay. So do we see the Acrobat Reader screen here now? Should say Module 2.2 IR spectroscopy. Can we see that?
Yeah. I just see a white line down the middle of the
screen. It was there and then it just kind of minimized itself.
Okay, let's try again then. I'm going to share again. Yeah, if I move it, apparently it, there we go. All right, can we see that?
Yeah, we can see it.
All right, great. Okay, so what I'm going to do is I'm going to go ahead and get down to here, and we're going to go ahead and do the slow version of annotation here. And I'm going to get my blue thing. So the idea here is that when we have all the different wavelengths of IR light coming through and it gets split and then it goes through the system here, and then the ones that are missing are the ones that we can detect our functional groups with. So the idea here is when light is absorbed, a bond vibrates and we can detect it. Okay, so let's move. Okay, and whoa. And so they get kind of fancy here. This particular one, oh, annotate, clear. All right. So they look really fancy, and they've got it to the point where all you have to do is basically put a drop of your liquid on a diamond crystal here, and you can take your spectrum. The sample prep for these materials has gotten so easy, and they have these huge libraries so that you can easily tell your compound from every other compound in the world by looking at the library and compare and contrast. So it's a very powerful tool, but again, it mainly looks for functional groups. It's very hard to assign an entire molecule for that, but you can definitely assign which functional groups are available and which functional groups are not. Okay, clear. All right, so let's move down to the next one. So the whole thing we need to think about here is that the wavelength that a bond absorbs at is related to its energy. Okay, so the idea here is that stronger bonds will vibrate at higher energies, meaning higher wave numbers. Okay, weaker bonds are going to have lower frequencies and lower energies. Okay, so let's look at that as a function. Now, atoms with less mass vibrate at higher frequencies than and higher wave numbers. Okay, think about that. If you have two heavy atoms and they're on a spring and they're going to move like this. Okay, so let's say that's energy 1. Okay, now if you had an atom like carbon and then a hydrogen on here, what it's going to do is that's going to actually vibrate much more quickly because the same amount of energy is going to move that smaller amount of mass. So what we're looking at is that when we have a heavy atom, light atom, we have very high frequencies because of the light weight. And then as we move down to where the atoms are approximately the same size, it's all about bond strength. Okay, and so we can actually think about those different things as a function of energy. Let me explain something too. When we talk about frequency, we actually use a weird term called wave numbers, and that is reciprocal centimeters. Okay, so in most IR spectrometers, we start at 4,000 reciprocal centimeters, or centimeters to the -1 power, and we go down to about 400. So that range from 4,000 to 400 is where we find most of our absorptions happening in these bonds. Okay, now let's take an example from that and look specifically at there. Let's look specifically at this set of atoms here. If we go from carbon and hydrogen, have that bond there, our frequency is 3,000 wave numbers. So that's a high frequency, right? Because we have a light atom and a heavy atom. If we switch hydrogen to deuterium, deuterium is the heavy isotope of hydrogen. It just has one extra neutron. It has one neutron in it. And look at the frequency drop. It's almost 1,000 wave numbers difference. So that just that change in that one proton changes the frequency. And then if we look at carbon-carbon, those are two heavy atoms, it drops all the way down to 1,200. So that's the effect of the mass on the frequency of these bonds. So anytime we have a hydrogen bonded to some atom, it's going to have a high frequency. And anytime we have like atoms, they're going to have a much lower frequency. Now let's look at the effect of stronger bonds. In the case of this carbon-carbon single bond, we had it at 1,200. So that's a low frequency. If we make that bond stronger, because it has a double bond now, so we're sharing 4 electrons, it actually comes up in energy. And if we have a triple bond, it comes up in energy again. So the mass isn't changing. The only thing that's changing is the strength of the bond. And we see that same trend when we go to carbon and nitrogen. We start at about 1100. Once we get that double bond for the imine, which we don't cover in this course, and when we go to the triple bond with the nitrile, it keeps going up. And that has everything to do with the strength of the bond. And likewise, if we have a single bond to oxygen versus a double bond to oxygen, we go from 1100 to 1700. Okay, so that's the effect of strength of the bond. Now let's look at some other common things we have. All of the ones with hydrogen on it right here are in these high frequencies. Notice all these ones on with hydrogen are almost like 2800, maybe 2900 to 4000. So that's where you should see all of your hydrogens on systems. And when we have like atoms here, these shift a little bit, but notice these are mostly mass. It has nothing to do with electronegativity. It's all about the strength of that bond. And notice all of these are approximately in the same range as well. And so the triple bonds are also in it. So those frequency bands are driven by their bond strength, okay? So clear out and all right. So when I say those bonds vibrate, we can also have the entire molecule vibrate as well. So the simplest way is just to have the two atoms on a spring and they vibrate back and forth. However, because we have other atoms, if you have more than two atoms, you can actually have the entire molecule. And so there's a bunch of different ways we can do it. We can have things where they're stretching symmetrically, like the first one. And then if one's going out and one's going in at the same time, then that would be an asymmetric stretch. All these different kinds of motions right here have different energies, and they show up in different parts of the spectrum. Okay. All right, let's continue. So this is the key thing you need to put to memory about IR right here. We have 4 ranges of functional groups, and you need to be able to identify which the ranges they are in. Notice when we start up here on the first one, we have the first band here is everything right around 3000 and above, okay? And that has the carbon hydrogens that go from about 2800 to about 3100. We have anything with an OH on it, so that would be water and alcohols. And that's a little higher. It's about 3000 to 3500. And nitrogen here is also about 3000 to 3500. Okay, so that means anytime we're looking for a functional group with a hydrogen on it, we're going to find it in this range. Okay, we don't see any hydrogen bonds in any of the other ranges. Okay, now the second area here, remember, we're going with the frequency increases with bond strength. So our next thing is our triple bonds. They're found right here, right around 2200 to 2300, 2100 to 2300. And that's where we find our alkynes and our nitriles. Okay. The next zone here is about 1600 to a little over 1800. And that's where we find our double bonds. Okay. All of our double bonds are going to be found in this range here. And then the last zone here is what we call the fingerprint region, because there's going to be a lot of fine detail, because that's where all those molecular motions show up with wags and bends and asymmetric stretches. And they'll also show up in this range. Oops, that's not a good color for that. But in this range right here, that's where we see all of those single bonds. So the key here is the high wave numbers are the high frequencies. The highest ones are the ones with those light hydrogen atoms. Then we go triple bonds, double bonds, single bonds, okay? That's the way to remember where these different things are going to be in these different zones. So even if you really didn't know what the compound was, you can say, hey, it has a peak in the 1600 to 1800 range. It must have a double bond of some kind. A double bond to oxygen, a double bond to carbon, or a double bond to nitrogen, okay? Does that make sense? That we have the reason for these is all about energy that they can absorb. All right, clear. And so let's take this kind of thing and put it to memory, and let's start looking for the different functional groups we find in an actual IR spectrum. Okay. So if we look at this one right here, if we just look at the structure itself has, oh, it's in white, that's why. Okay, the structure itself has, what kind of functional group does it have? Ruben, did you have a question? Your mic's on. Oh, okay.
No, sorry. Sorry about that.
All right. So yeah, so we have an alcohol here. We have a carbon-oxygen bond, and we have carbon-carbon bonds, but we also have a carbon-hydrogen bond. Remember, we have our understood hydrogens here. So we need to look for a carbon-oxygen bond, a carbon-carbon bond, carbon-hydrogen bond, and an oxygen-hydrogen bond. So let's look at the hydrogen bonds first, because we know they're going to be really high. So here we have, in that range of 3,000 to 3,500, we have this broad peak. This is very common for alcohols right here because of hydrogen bonding. Okay, hydrogen bonding is when you have an acidic proton on an oxygen that can bond to neighboring lone pairs. So you'll likely see this very broad peak for an alcohol or a carboxylic acid, which also has that. The next thing we see is these CHs. And notice it's not just one peak, because we have different types of CHs. This hydrogen here, this tertiary hydrogen here, is different than this primary here and this secondary here. So they actually have slightly different frequencies, but they all show up in the same range. And then right here, we have our carbon-carbon bond and our carbon-oxygen bond. They're probably right together somewhere here. And then we have our fingerprint region. Notice how there's a lot of different peaks there. That's all those different wags and wiggles and rocking motions that we see in those other systems. So we really don't try to identify functional groups based on the fingerprint region, but it's great when you have to compare it to previously done samples. Okay, so all I did here was look for the different functional groups based on their energy levels. Okay, let's do that same thing on the next one right here with this amine. Okay. With the amine here, we're going to have those same carbon-hydrogen bonds. We're going to have those same carbon-carbon bonds, but now we have a carbon-nitrogen bond and a nitrogen-hydrogen bond. And again, it's going to show up in that same region. It's a little broad right there. We have those same peaks for carbon-hydrogen, and we have our carbon-carbon peak somewhere here and our carbon-nitrogen peak right here as well. So we have been able to find each and every type of bond we have there. Now, there's a problem here if you want to say, oh, do I or do I not have this functional group? And if there's a peak missing for your bond type, it can't be that functional group. So you have to have the peaks for each of the functional groups. That's what we're looking for here in an IR spectrum, because those bonds have to absorb the energy. Okay, so let me tell you some subtle things about amines. Okay, with the amines, we have a choice for a primary amine, a secondary amine, or a tertiary amine. Okay, so in the case of the primary amine, we have two hydrogens on there, and it usually shows up as two peaks because they're not exactly equal. Okay, so when we have a primary amine, what you'll see is two peaks in that region there, and that's signifying that you have those two hydrogens there. Alcohols will only ever have a single broad peak. They will never have this fine peaks that you see here. So notice that peak shape is different than an alcohol peak. The alcohol peak is going to be very broad. The amine peak is going to have that sharper peak, but in that same region. Okay. If we remove one of those hydrogens, we now get our peak going down to one peak because we only have the one hydrogen. And then if we go and make it a tertiary, so we have no hydrogens there, the peak goes away. So this is a great way to say, hey, I have an amine. I wanted to make it a secondary amine, and I saw there's a shift in the IR. And then I turned it into a tertiary amine, and I saw another shift in the IR. So we're identifying functional groups, not absolute structure. Okay. And then, so there's other cool thing here is that we can identify different types of hydrogens based on the carbon they're bound to. And the reason we can do that is because the bond between the carbon and the hydrogen has different hybridizations going from alkyne to alkene to alkane. So in the case of our alkyne right here, we know that our carbon, okay, draw. There we go. All right. Our carbon is sp hybridized here, and so it has a shorter bond to hydrogen. If it has a shorter bond, that leads to a higher wavelength because it has a higher bond strength. So notice that the range for carbon was like, for the carbon hydrogen bond was 2800 to about 3300. That's because the alkynyl hydrogens are higher at the 3300 part, and they're a nice sharp peak. Now let's look at the alkenes right here. That's an sp2 hybridized carbon going to a hydrogen, and so it's slightly longer bond length, slightly lower energy, and our frequency shifts down again right here. And then if we go for our alkanes right here, those are our sp3 hybridized. Those are going to be our longest bond lengths and our lowest energies. So that means we can tell the difference between alkynes, alkenes, and alkanes just by looking at the types of hydrogens we have in our system. Okay, all right. So let's look at that, and let's see if I can blow this up a little bit. There we go. We're going to do it that way. Okay. So let's look at that alkyne right here. And what we see is that we have in this alkyne peak, we have we have sp3 hybridized hydrogens here. So those are alkane hydrogens. But now we also have this hydrogen right here at the alkyne peak. Okay. This hydrogen at the alkyne peak is different than all the other ones, so it shows up here at 3300. And it's because of that shorter bond length and that stronger bond, so it's higher frequency. All the other CHs show up just below 3000. Okay, so 3000 is a good number to remember because all alkane protons, all alkane hydrogens are just below 3000. The alkenes are just above 3000, and the alkynes are right at 3300. So that's a good way to differentiate between an alkene, an alkane, and an alkyne just by looking at where the peaks show up in the IR. So let's go ahead and look at that same compound, but instead of being an alkyne, we have an alkene. So we have 3 hydrogens hanging off this alkene right here, and they show up a little bit higher in energy, just above 3000. All the rest of these right here are the ones that show up below 3000. Okay, and if we take away the alkene and the alkyne completely, notice on this one right here, all of the peaks are in below that 3000 mark. Okay, so that means we have a good way to get our alkynyl peaks, our carbon hydrogen peaks aligned in our system. Now, we have one other kind of carbon hydrogen, and I'm going to go ahead and undo it, is the hydrogen attached to a carbonyl. So that's an aldehyde, right? So that's different than any of these other ones because that carbon is double bonded to an oxygen. So that changes the nature around this peak, and it will make it shift into lower energy because it is a longer bond. More of that energy is bonded to, it's still an sp2 carbon, but it's a longer bond. And so our usual peak for these show up right around 2750. So if you see a peak at 2750 to 2800, think alkyne. It's the only thing that really shows up as a sharp peak in that range. Okay. So that's all 4 types of carbon hydrogen bonds we have available to us with our functional groups. Okay, questions on that? All right, I'm going to clear all drawings and
You said 2750 to 2800
correct.
alkyne?
Is the aldehyde. Yes.
Oh,
So
okay.
that's that hydrogen on the carbonyl of the aldehyde.
Okay.
Okay. And that is the only, and those are all 4 types of carbon hydrogen bonds we have available to us with our functional groups. Okay. So let's move on to other functional groups like the ketone. In the ketone, let's look at how many different types of functional groups we have here. So in this case here, we have, I'm going to go back to red. And if we look at right here, we have aliphatic hydrogens of alkanes right here. And then we have the carbonyl here. Those are the only 2 functional groups we see. Oh, we have carbon-carbon bond, we have a carbon-oxygen double bond, and we have a carbon-hydrogen bond. So we need to look for all 3 of those types of bonds to make sure we have what we have. Now notice right here, these are our carbon hydrogens and they're below 3,000. So that means they're all aliphatic hydrogens. Now our carbon-carbon, our zone here from 1600 to 1800, 1600 to 1800, that's where we find all of our double bonds. Our carbon-carbon double bonds, our carbon-oxygen double bonds, and our carbon-nitrogen double bond. And so we have a nice strong peak. In fact, carbonyls are usually very strong peaks in this range right here. And this is a ketone and it shows up around 1700. If we attach different things here, this peak shifts up and down, and I'll explain why that happens later. And then we also have our carbon peak down here and some stuff in the thing. So we looked, we thought, oh, I have a ketone, so I must have a peak in that 1800 to 1600 range. And in this case, we do. So we do have a ketone. All right. So I said that carbonyl shifts around, okay? And I want to tell you why here. So in the reason that shifts around is because this bond right here is the one that's absorbing in that range, okay, right? But the amount of electron density on the oxygen changes by what the group is bonded to it. If it's a carbon, it doesn't really pull much electron density to it. However, if you have some other electron withdrawing group, like a halogen or a salt or something, then you can get a resonance structure where you have charge separation. You have a negative charge on the oxygen and a positive charge on this electron withdrawing group. And because of this, you've changed the nature of this bond. It is no longer exactly a carbonyl bonded to 2 carbons, and therefore it shifts, and it can shift down or it can shift up, okay? If it shifts down, if it's a strong electron withdrawing group, it's going to lower the energy and lower the frequency. If it's an electron donating group, it's going to shift up. So what does that mean? How can we, how do we visualize this? Okay, so I have here. So I'm going to compare all the different carbonyl type compounds and show you from their highest to their lowest frequencies, okay? So the highest frequency we're going to have is with the strongest electron withdrawing group right here. Chlorine is our strongest electron withdrawing group because it has our highest electronegativity. If it does that, it means it's going to change the nature of the bonds, and it is going to have it's going to have the weakest delocalization on, which means it has the strongest carbonyl bond. It has the strongest carbon-oxygen bond. Because now in here, we're just sharing electrons. Here we have a separated charge. Now we have our charge attraction, giving it that highest frequency. So we have a chloride or any halogen next to a carbonyl compound, we have the highest frequencies, okay? Now in the effect of esters, we have a little bit stronger. The electron withdrawing of the oxygen, the electronegative oxygen, is a little stronger than the resonance factor. And so we get, again, charge separation, and we have our peak at the 1750 to 1735. Now let's go to our hydrogen. Our hydrogen is about the same as carbon, and therefore it actually has to do the electron withdrawing group from the alkyl group, and that shifts it again to this 1740 to 1725. Here in the ketone, we have 2 carbons, allowing it to donate into that carbonyl carbon, and that shifts it in that range we saw, that 720 to 710 range. That is right where you're going to see ketones. And think about it, that carbon-carbon bond is not that very strong, and it's just, I'm sorry, the carbon-carbon bond is not very polar, and so it's not going to donate or withdraw too much. And so that's what we call our center point. Everything is going to go above or below that. In the case of amines, our amides, we have a strong resonance presence. And in the strong resonance presence means we have a lot more of the charged species this way. And so that delocalizes our carbonyl, and that shifts our frequency down below 1700. And then the most delocalized possible carboxylic acid we have is the carboxylate salt. Okay, so in the case of the salt here, this carboxylic acid salt, this is completely delocalized across both of these oxygen, and has the lowest frequency possible at this 1600. And then it does have this frequency down here, but this is typically in the fingerprint region, so we don't really see it a lot. But do we see why the group on that carbonyl will shift it along those bands? Our lowest would be about 1600 for our carboxylate salt. Our highest is going to be for our acid chloride. Our aldehydes are higher than our ketones, and our ketones are right in the middle at that 720 to 710. Okay. So that being said, let's look at some derivatives here and see if we can see them change. Okay. So let's look at this with a right here. So we're going to have aliphatic hydrogens, we're going to have carbon-carbon bonds, and we're going to have a carbon-oxygen double bond. Okay, so we should see our carbon-hydrogen bonds up here. These are our carbon-carbon bonds over here, and this is our carbonyl bond right there in the middle at 1718. Okay, so that tells us our starting point right there for that. Okay, so now if we take this compound, and this only had aliphatic hydrogens, and now we add an alkene to it, how does it change? Well, the first thing that changes is these are all of our alkane hydrogens, but notice we have a peak up here. That's the alkene hydrogen. That's this hydrogen right here on the double bond. So we already know we have an alkene because we have a peak above 3000. But look what happened to our carbonyl. Our carbonyl shifted down. And we also see the presence of a new carbon-carbon bond. The reason it shifted down is that because we have a double bond next to here, we're actually pulling electron density away, giving it a place for it to resonate, have resonance for it, and it shifts down to just below 1700. So it's shifted down over 20 wave numbers just because it's in conjugation with that double bond. But the cool thing is we can also see our carbon-carbon double bond and our carbon-carbon single bond. Okay, questions on that? So we're looking at our carbonyl and watching it shift around as we change functionality. Okay. And there's an example of why we shift it down here is the resonance characteristic that we can draw competing resonance structures to delocalize that, that double bond over that. And that's what's shifting it down in energy, just like the carboxylate salt. Okay. All right. So we can kind of tell the difference between cis and trans, or E and Z on these. But let's see. Oh, yeah. Okay. So sometimes you actually will not see the carbon-carbon double bond. Okay. The times you don't see the carbon-carbon double bond is when it's symmetrically attached to the two same types of atoms on there. And what this means is the bond, the carbon-carbon bond, is not very polarizable, and it doesn't absorb the energy very well. Okay. So if we had a trans system, if you look at it in space, it is symmetrical as far as where its dipole is, and therefore we don't necessarily see it. However, In the case of the cis right here, because both of the groups are on the same side, we actually have a net dipole in one direction, and that allows us to see that carbon-carbon double bond, and in this case, it's at 1668 right here. Now we can intensify that by changing the groups attached to it. So we have a chlorine on here and a methyl group here. So that means we have a much more intense dipole motion, and we have a much more intense dipole moment, and that means the peak gets bigger, okay? So in alkenes, it's very important. If they're unsymmetrical, they will show up much more strongly than otherwise. All right, clear drawings. Yeah, I like doing it on my iPad better. Okay, so let's look at those triple bonds, okay? So we have a couple things to look for with our triple bond. If we see our triple bond, we're going to look at it and say, okay, is it symmetrically substituted on both sides? Is there a carbon on both sides of the alkyne? If there is, that means it has a very low dipole moment. We're gonna have a very small peak at that 2000 range. Okay, remember our triple bonds are in that 2000 to 2200 range. And we see a tiny little bond here because we have a carbon going this way and a carbon going that way, and that cancels out the dipoles and we don't see it. Notice we also don't see anything here because we've taken the hydrogen off the alkyne. Now, if we put the hydrogen back on the alkyne right here, we're going to see that alkyne hydrogen at 3300. And now that we have a hydrogen on this side and a carbon on that side, we have a net dipole motion going to the carbon, giving us a stronger peak right here. And then just like that, we always get a strong peak for nitriles because nitrogen is more electronegative than carbon. So the nitrile peaks always show up and are always stronger than alkynyl peaks because of that polarization of the bond. So if the requirements for IR is the bond has to be there, the energy associated with the absorption where it shows up in the spectrum is all about how strong that bond is or whether or not it's bound to a light atom. And then the intensity of the peak is all about the polarizability of that, or the net dipole of that bond. So in the case here, we always have a permanent net dipole in that direction. And so we have the strongest bond in that region. Notice it's right just at 2200. On the second graph, what's the peak way up here? It's probably just some kind of artifact or overtone. That's not an assignable peak within our system. Okay. Oh, there's a question there what the little peak up here was. Clear all drawings. So that, I wouldn't call that an assignable peak. Like all these little peaks here are probably just vibrations of other things. We're looking at the really intense peaks to help assign a functional group. Okay, so let's move on to some things, and let's just look at the types of bonds we have. We haven't talked about benzene very much, but the types of bonds we have are, in this case, we have carbon-carbon single bonds, carbon-carbon double bonds, and we have hydrogens on carbon-carbon double bonds, and we have hydrogen on carbon-carbon single bonds. So the first thing we look at is right here. We draw our line right at 3000, and notice we have peaks above and below. That means we have hydrogens on sp2 carbons and hydrogens on sp3 carbons. Okay. Now, we also have our carbon-carbon double bond here right at 1600, and we have our carbon-carbon single bond here. Now, what's really neat is because benzene is in this circular pattern, we have this pattern right here. And it's typically 4 right here called the overtones, okay? So that is, these peaks here are indicative of having a benzene ring or a phenyl group on a system. We'll see this peak, and sometimes we won't. It won't be very strong because it'll be symmetrically substituted, but we'll see these overtones here. That's an indication of those bonds. Then of course, carbon-carbon single bonds here. Okay, let's, okay. So let's talk about intensity. I told you intensity has to do a lot with the polarization of the bond. The more polarized the bond is, the more likely it is to absorb energy. So let's look at that as a function of the different functional groups. So OH, NH, OH has a very strong and broad peak. Let me blow this up. There we go. Right here, OH has this very broad and strong peak because of that strong, the frequency is because of vibration, but the intensity is because that's a very polar peak and it can hydrogen bond. Now, nitrogen is not as strong, but notice when we had two hydrogens, we had two peaks. And it's because there's they have a stretching peak, and each hydrogen can stretch independently. So when we have a primary amine, we can get two peaks there. If we have a secondary amine, we can get one peak there. But these are typically moderate in strength because the electronegativity of nitrogen difference with hydrogen is not as great. That's a slightly longer bond, and so it has a slightly lower energy. And it's slightly less polar, so it has a lower intensity. And notice the CH2 right here, it has those two peaks there. Those are those two peaks independently vibrating together. Our alkyne is variable because it depends on the polarization of the system. Our alkenes are variable because it depends on the polarization of the system. And our aromatic protons are also variable. So they can be very high or very low in intensity some of the time. Our alkyne peak is usually strong and very narrow because that is a very polarized bond and you can see it easily. Okay. The aldehyde is usually a strong bond right here at 28 and to 2700. And it's strong because it only has one vibration mode and it's a very polar bond. Our carbon-carbon triple bond is typically weak and can even go away sometimes. Our carbon-carbon bond varies a lot. Okay. Can you go over the difference between the stretching and the bending on NH? Okay, so in the case of NH, the stretching peak, which is the hydrogen stretching away from the air, is the one we identify at the 3000 level. The bending peak is actually down very close to the fingerprint range. And so we usually don't identify an amine by the bending mode. We usually just identify it by that stretching mode. Okay. I had a question about that. So, all right. So nitriles are variable, but they're typically fairly strong and fairly narrow. Okay. The carbonyl compounds here, all the carbonyl things, the carbonyl peak there is usually very strong. Think about it. You have a carbon oxygen, that's a very polar bond, very polarized bond. So they always show up as strong. And so notice all of these, the ketones, aldehydes, amides, carboxylic acids, they just shift position based on their ability to have resonance structures, but they are all very strong. The carbon oxygen peak is strong because it's polar, and the carbon fluorine peak is strong, but it's in that fingerprint region, so it's very hard to see. Both of these are in the fingerprint region, so it's hard to see. Okay, so that's all about how to look for intensity on those peaks. Okay, so let's compare these two with intensity to see how that works. Okay, so in the case of, we're going to compare methanol to formic acid, and we're going to look at how the different structures are different. So in this case here, methanol has an OH on it, and then it has just aliphatic hydrogens. So if we draw our line at 3000, we'll see that we have those CH3 hydrogens are here. These are our OH hydrogens, and notice it's big and broad because of hydrogen bonding. And the only other peak we have here, because we don't have any carbon-carbon peaks here, we have a strong CO peak. Okay. So notice this is down right around 1000. So it's not a carbonyl. A carbonyl would be way up here. Okay. So it's definitely our single bond to carbon peak. Now, let's compare that to formic acid. Formic acid has this carboxylic acid right here. So we have an electronegative atom on our carbonyl peak, and that's going to take it right here at around 1727. Remember, ketones are like 1720 to 1710, so it's above that. And because of hydrogen bonding with the carboxylic acids right here, this peak gets very broad. And actually, it kind of covers up that hydrogen for this peak right here. So they're barely showing up here, but they're hidden under this big, broad OH peak. This is very common in carboxylic acids to have a much broader peak and to come out past 3,000. But then we also have, so we have identified all of our functional groups. This right here is probably the carbon-oxygen bond for the CO here, right here. And notice it's a little bit different here because we have a hydrogen on it. It's going to be a slightly different, oh, no, because it's bound to the carbonyl. So that's why it's slightly different. But so this is our CO peak. This is our C double bond O peak. And then this is our OH peak, really broad. So see how just changing the structure will show up in the IR because of the different functional groups absorbing different energy ranges. I don't like that I have to put away my thing. All right, so now let's figure out a method for analyzing an IR spectrum, okay? So you can sit there and think about, oh, every little single peak and then drive yourself crazy. So don't do that. So what we want to do is we want to identify the most intense absorption peaks first, especially those above 1,000. Okay, so the reason we do that is those are the strongest and those identify most of the functional groups very readily. Okay, then we're going to assign the peaks that are most likely functional groups. When we look at in most intense absorptions, they can be very, some of them can be small, but most of them should be very well pronounced. Then we have to consider what functional groups are there, what kind of things are there. Do you have double bonds or rings or something like that? And then you kind of look at a symbol, all the different types of functional groups that can be in that molecule. So let's use that method and try to identify a couple of them. Okay, so let's go back here. So in this peak here, we wanted to identify this. We know it right away from this peak here that we had an OH. So that told us we had an alcohol or we had something else. It also told us we had some aliphatic hydrogens right here. So we have aliphatic hydrogens here. And then the only other major, notice that these are fairly nice and straight. These right here are, not strong enough to identify right there. And then right here, this, because it's above 1,000, we have a nice strong peak. So we can go through and identify them peak by peak by peak to get them into our assignment. All right, so questions on IR. And again, I want to stress that don't try to memorize where things are. Look at this chart here. The things with hydrogens on them are in this 27 to 3,500 range. And just know the difference between the alkane hydrogens, and alkyne hydrogens, and the different kinds of OH and NH. The next band over here is this 21 to 2,300. Has to be triple bonds. If you have something in that range, it has to be a triple bond. The next range over is the 1,600 to 1,800 range. You have to have double bonds in that range, okay? And then we can occasionally see some carbon-carbon bonds and carbon-oxygen bonds in this region. But once they get too far below 1,000, it makes it difficult to call those strong peaks and very intense peaks, okay? So by understanding why the different types of functional groups are in the different ranges, I think it makes it easier to remember and understand. Okay, questions on IR spectroscopy? So again, the reason I do it right here is because we just learned all those functional groups and I wanted to show you that. You do not need to know the wavelength or frequency calculation for the exam, What I'm going to do is say, here's the spectrum. What functional group do you think's here? Okay, that's what I want you to get out of this. To number one, say these functional groups are real and we can see them with light, and that they have ranges, and they are because of that bond energy that puts them in those specific ranges. Okay. All right, I'm going to stop sharing and move back over to my iPad so we can continue on with acids and bases. Go ahead and grab something to drink. Protein shake for me. All right, so I'm going to go ahead and take that away, close those tabs, and I'm going to open my iPad again, except there we go, and I'm going to pull up our, nope, files, there it is. And we're on acids and bases. There we go. And we had talked about Lewis acids. We talked about Bronsted-Lowry acids and bases. We've talked about how we know which way the equilibrium lies. Oh no, we finished acids and bases, didn't we? We were on, no, we finished, no, we're on acids and bases, sorry. Another class. All right, so, all right, let's get it up to there. And we got up to the point where we said there were 4 things that changed or affected the acidity on different compounds. Okay. All right, can everybody see the slide that says what makes one acid more acidic than the other?
Yeah.
Yeah, okay, great. Okay, so we ended here. We talked about that equilibrium constant is all about which way it lies. And we know which way it lies is based on which acid is the weaker acid. It's going to go toward the weaker acid and weaker base, always, okay? So what tells us which is more acidic or less acidic is these 4 factors. The first thing we're going to talk about is the electronegativity and the size of the atom, because they kind of balance each other out as far as increasing or decreasing acidic strength. The next thing we have is resonance or delocalization. If you can spread that charge out over more atoms, it's going to be more acidic because it's becoming a weaker base. If you also have inductive effects. If you have an electron withdrawing group or an electron donating group that can pull electron density through those bonds, it will change the acidity, and the hybridization of the atom or the type of orbital will change the acidity of that acid as well. So let's go to talk about them one at a time. Okay. Okay. So the first thing we're going to talk about is the stability of the conjugate base. Okay. So the stability of the conjugate base means if it wants to be an anion, like a chloride ion or something like that, it's going to want to be in that conjugate base state. Okay. And more electronegative atoms tend to be or have a greater ability to stabilize that negative charge. Think about fluorine. Fluorine has an electronegativity of 4. It wants to be a negative charge if at all possible, but it will share electrons if there's a small enough electronegativity difference. Okay, but it really wants that. Okay, and just like chlorine and bromine, they all are nice, stable, happy anions. So that means that they're going to be more acidic, and that conjugate base is going to be more stable or less basic. Okay. So we want to look at it that way. And so we can see that trend also in the group 2 elements as well. Okay, so aside from the hydrogens, we have other things that we can have these, I'm sorry, aside from the halogens here, right here, that will increase the base strength. We also have decreasing electronegativity as we go here. So let's look at just the decreasing electronegativity along our group 2 materials here, around this bond here, and look at its effect on acidity. So the first one right here on that row 2 is our fluorine right here. It has the most polar bond, and the fluoride has the highest electronegativity. So in theory, this should be the strongest acid of the set because of that electronegativity. Okay. If we move over one, that's going to make the hydrogen on this oxygen atom, and in this case of alcohol, less acidic than the hydrogen on the hydrogen fluoride. And then when we move over one more to that, that makes going to be, this is going to be less acidic than the one that was the oxygen. And our next one over is our carbon, which is going to be less acidic than our nitrogen. Okay. So, and it has everything to do with that idea that the carbon is less stable as the anion than the nitrogen would be. The nitrogen's less stable as the anion as the oxygen will be, and the oxygen is less stable than the fluorine because of that difference in electronegativity. Okay, and I think, so, and if we remember a couple of our things right here, HF is right around 0. Our methanols, pKa is 16. Our amide, our pKa is 26. And our alkynyl group here, our pKa is 50. So we have it going from 1 all the way down to 50, just going down the scale, just going down that first row. That change in electronegativity is the major reason for that change. Okay. So the next thing we have to look at is size, okay? Because size also helps disperse that negative charge. So if we think about a fluorine, it's a very small atom, and when we make it charge-wise, it gets even smaller. So we have very little surface area to spread that negative charge out over. As we go up to chlorine, that's a much bigger atom and can stabilize that charge more, bromine more, and iodine even more. So while the electronegativity is dropping as we go, the fact remains that the ions are getting much, much bigger, and they can stabilize that extra negative charge there, making them more stable. So that's why if we look down the acid strength of the series of HF to HCl to HBr to HI, this is the weakest acid, is HF. It's not even fully dissociated in water when we put it in water. So it's actually a weak acid. It's not a full strong acid. However, all of these are what we call strong acids. They fully dissociate in water. And the reason is that they're getting fluorine's really small, chlorine gets bigger, bromine gets bigger, and then iodine is huge, which makes iodine the strongest acid that we're going to work with here. The hydroic acid is the strongest acid, but it's all about the size, not just the electronegativity. Notice our electronegativity is dropping. So we have that balance. If they're atoms of all approximately the same size, electronegativity dominates. That's going down this row. If they're different sizes, size dominates on that. And so when we think about stronger acids, that makes them more stable bases, weaker conjugate bases. Okay. And so the weaker conjugate base means it's going to cascade down to that product when possible. Okay, so let's actually put some actual values on these things and compare them so that we can see the difference between electronegativity and the difference in size. Okay. So I'm going to pull that part up here. So HF, I said it was not a strong acid. It's not below 0, and it has a pKa of 3. Okay, that's close. And as we go to water, we had a pKa of 15. The alcohol was 16. The amine is 36, and the carbon is 50. Okay, and most of them are 50 to 55. Now, that all has to do with the change in electronegativity because they're all about the same size. They all have that number 2 orbital energy level that they're filling those electrons in. Okay. The more acidic a compound is, the more stable the conjugate base is. Okay. So in other words, the more stable the conjugate base is, the more acidic it is. So if you have a big fluffy anion here, like iodine, it's going to be more acidic because that conjugate base is going to be more stable. Think of it as always, if the conjugate base is more stable, it's going to give up that proton much easier. Okay. So if we look at HCl, HBr, and HI, they increase as we go down there, and that's all by size, okay? So, and the same is true for our series here. If we go down one, we have oxygen, sulfur is larger than oxygen. And so the size is what's making it more acidic because our number's going down. Selenium is more acidic and tellurium is even more acidic right here. So it works with all the different elements, but the general idea here is that size is the dominant factor here and electronegativity is the dominant factor along the same size group of atoms. Okay, questions about size or electronegativity as it affects acid strength? Okay, so now let's go to our second effect. Our second effect is what we call inductive effects. Inductive effects are where we can partially or fully charge charges. You stabilize the stability of partial or full charges by electron donating or withdrawing groups, meaning that if you can pull electrons away from something, it means it'll have less of a negative charge. Okay, so let's see how that works. Okay, so if we take a compound and just look at it and say, okay, let's call this our baseline compound. This is a carboxylic acid derivative, 1, 2, 3, 4. So that's butanoic acid, okay? And butanoic acid has a pKa of 4.83, okay? So this is its equilibrium right here, constant, and it's going to have it in equilibrium because we have a pKa. It's not a negative number. And so that's our starting point, okay? However, if we put an electronegative atom on that group, on that carboxylic acid, what's going to happen is the pKa is going to go down because this electronegative atom is going to pull electrons through this bond. It's going to pull electrons through this bond. It's going to pull electrons through this bond. It's going to pull electrons through this bond, pulling electrons through this bond, making this hydrogen ever so slightly more acidic. Okay. So notice it's pulling electron density through 1, 2, 3, 4, 5 bonds to do this. Okay. But we can still measure the difference. Okay. So let's move it a little bit closer. Let's say, so it only has to draw that electron density through 1, 2, 3, 4 bonds right here. We see another drop in the pKa. Okay. The closer that electronegative atom gets to your carbonyl, the stronger the effect because you are pulling electron density through fewer bonds. You're pulling it through bonds, not through space. That's what we call it, the inductive effect. It's inductively pulling electrons through bonds. Now, if we move it over one more, such that chlorine is right here, and only has to pull through these 2 bonds here to make that hydrogen more acidic, we actually end up with dropping the pKa even lower, making it an even stronger atom. I'm sorry, a stronger acid. So the idea here is if you have an electronic drawing group close to your carboxylic acid, it's going to increase its acidity because it's taking away some of that negative charge. Okay. Which means if we had an electron donating group, it's going to make it less acidic because it cannot stabilize that charge as much. Okay. So let's look at it as an effect on different little groups on our carboxylic acid. Now we're going to start with our basic carboxylic acid right here, acetic acid here, and we're going to change some things. The first thing we're going to change is we're going to change the nature of the electronic drawing group. Okay. Okay. So in this case here, fluorine is the most electronegative. Then it drops to chlorine, bromine, and iodine as far as electronegativity goes, right? Which means fluorine should be the most acidic and have the lowest pKa. Okay. Now, since chlorine is not as electronegative, it will not have it as big an effect. And what we see here is that yes, the pKa is coming up. It is less acidic when we have that chlorine on there. Bromine again is less electronegative than chlorine, and therefore we see another jump. And we see our last jump with iodine. So this is all about that inductive effect. Remember, those halogens are not trying to stabilize that negative charge. They're trying to pull electron density away from the carboxylic acid. And that's why we see this trend. Now, the inductive effects are actually kind of additive. The more electron withdrawing you have, the greater the effect. So in this next one here, we have, just a hydrogen here. So that's our baseline at 4. By putting 1 chlorine on there, which is, notice it's the same as up here, you drop the pKa, you increase the acidity. Okay. But what happens if you add another one? You can now withdraw more electron density because you have 2 electron withdrawing groups here. And you drop the pKa and you increase the acidity. And then by adding another group here, we now have 3 things pulling away. We are going to drop the pKa and increase the acidity even more. Notice this is almost 0. That is like the strongest organic acids we can have are these ones with carboxylic acids with electron withdrawing groups next to them. Okay, so do we see why the acids get stronger through this inductive effect? Okay, so let's talk about another electron withdrawing group right here. So what we can do is a nitro group is also a very strong electron withdrawing group. And it's not because it is more electronegative, it's because when we draw the resonance structures and draw our Lewis dot structure and assign formal charge to the nitro group, no matter which resonance structure we're in, right here, we have a positive charge on nitrogen and a negative charge on the oxygen here. No matter which way we draw that thing, our neutral nitro group has a positively charged nitrogen. Because that charge is positive, it's a strong electron withdrawing group that would increase the acidity of adjacent hydrogens. Okay. So we have fluorine halogens as strong electron withdrawing groups. We also have the nitro group as a strong electron withdrawing group. Okay, so let's see how that affects it. Well, if we take an alcohol here, instead of a carboxylic acid, we're going to start with ethanol, and so our pKa is right around 16. Okay, by adding a fluorine, 1 carbon over from our oxygen here, we've actually dropped it down to 14, so that we're making it more acidic because of that electron withdrawing group, because of that fluorine there. Okay, however, the nitro, because this is neutral and has a formal charge of 0, this is neutral that has a formal charge of +1. It actually can pull more electron density and therefore makes it more acidic. So our alcohol here is becoming more acidic than the fluorinated version or the regular version. And it has everything to do with that nitro group being that strong electron withdrawing group. Okay. So there's also a solvation effect on this. And so in water, negatively charged conjugate bases are also stabilized by the solvent. The solvent helps to disperse the charge. However, if the conjugate base is poorly solvated water due to unfavorable interactions, like it has some hydrophobic sides to it, the equilibrium shifts to the reactant, making the compound less acidic. So as an example of that, let's take the carboxylic acids here again, and this one in the middle here, this is our acetic acid right here. And if we take this methyl group off and put a hydrogen on there, we have what looks like an aldehyde, and we have a carboxylic acid. So we call that formaldehyde, or I'm sorry, we call that formic acid. And by taking the carbon away and adding that hydrogen, so we can't donate much electron density, it actually becomes more acidic. Okay, and then it's also very polar and it has hydrogen bonding and dipole interactions. Right here, this has our nice hydrogen bonding and dipole interactions, but it has a very small R group. By adding another 2 more methyl groups to this, it's starting to get a little more like a hydrocarbon, right? We have 3 carbons with hydrocarbon character and only 1 carbon with a polar group on it. And notice that the acidity drops. Okay, it's becoming less acidic in water because we have this area here that doesn't want to dissolve in water. And if we add a 3rd group here, this is becoming very big, very hydrophobic on that end. and the acidity drops again. Okay, so that's because it has a less favorable interaction with water, and it does. Okay, and this is the same is true for alcohols. If you do this in alcohols as well, as they get bigger and bulkier or longer, they become less and less acidic. All right, we've got about 3 minutes left. Let's kind of look at that interaction again right here and show you why that big bulky group there makes it less acidic in that system. So we're going to compare the two extremes. We're going to compare the formic acid right here. And when you have that formic acid associated in water, you have lots of opportunities for hydrogen bonding. Notice all the water molecules here are hydrogen bonding with each other, but then they can hydrogen bond with the formic acid, and the charge can be balanced over multiple hydronium ions and water ions. So this is a very strong interaction. There's a bunch of different hydrogen bonding opportunities for you here. Okay. However, when we go to that trimethyl version of it right here, we now have a big non-polar group right here. Okay. And so that means that entire half of the molecule can't have any hydrogen bonding interactions or dipole interactions because it's non-polar. So that means only this little teeny half of the molecule can actually do any kind of interaction with the water. Okay. So notice here we can, hydrogen bond over here, we can hydrogen bond over here. There's a lot of more opportunity for things to come in here. But once we get to that big bulky space, we're blocking a lot of those possible interactions, and therefore it's less likely to give out that proton, and therefore it's less acidic. Okay. All right. So let's see. All right. We're right here at 9:20. I'm sorry for the technical difficulties. I will try to figure out how to not do that in the future. And so I'm going to pick up on the delocalization effects on Monday. All right. So I'm going to go ahead and stop sharing, stop recording. And if you want to stay behind and ask a couple questions, please do. Stop sharing.